In an earlier video, we were asked to find the Thevenin equivalent at the input interface of a circuit. Here, in this circuit, we're asked to find the Thevenin equivalent at the output interface between these two terminals here and here. And we recall the Thevenin equivalent consists of a simplified circuit consisting of one single voltage source connected in series with one single resistor. The IV relationship is given by this equation here, where we want to find the current through RT given as VT minus V divided by RT. And then solving for V, which gives us our voltage as a function of current, V is equal to VT minus RT. And this is the form of the equation that we want to find when we derive the Thevenin equivalent seen by the terminals across here and here with respect to the load. So looking back at this circuit. Okay, in this circuit, the controlled voltage Vx, which appears across an open circuit between, let's say, nodes A and B, as I labeled here. And by the fundamental property of node voltages, we could see that Vx is simply the difference between voltage at one end at node A and at the other end at node B, but that's just VO. Now when the load is disconnected, we could see that the input source is turned off. That is, Vx is equal to 0. And that the dependent voltage source, mu Vx, shown here, acts like a short circuit, and the Thevenin equivalent resistance, looking back at the output port, is simply RO. And that's when this is turned off. However, when we connect the load and then the input source is turned on, the sum of the currents at node B leaving is given as follows. So at node B, we have VO minus mu Vx divided by RO. And that's basically the voltage difference across RO. And when you're using Ohm's law, we divide by RO. That's the current. So the current's leaving. There's no incoming currents going into node B. And so what's leaving is the current through RO, as I described here, plus IO is equal to 0. Now we use the relationship that we just have for Vx, which is equal to Vs minus V0, and we substitute it in here. So that implies that V0 minus mu, substitute for Vx, so Vx minus V0 all over RO minus IO is equal to 0. Now we solve for VO, and that's equal to mu Vs all over mu plus 1 minus IO RO mu plus 1. Now we compare this equation for the Thevenin equivalent with this equation, and that we see that Vt is equal to mu Vs mu plus 1, and that RT is equal to this right here, where RT is equal to R0 divided by mu plus 1. So our relationship for Vt is given as this equation here, and RT is given here. Now the circuit is basically a model of an op-amp circuit called the voltage follower. The output resistance, however, for a general purpose op-amp is around 100 ohms. So RO for a general purpose op-amp is about 100 ohms. And the gain for an op-amp mu is very large, which is about 10 to the 5th. And thus for an active Thevenin resistance of the voltage follower is not really 100 ohms, but is 100 ohms divided by this mu factor plus 1, which results in a very small output resistance of a milliohm, which basically is what we want, is to have a small output resistance so that all of the voltage delivered by our source is delivered to the load and very little is dissipated at our output resistance. Now finally, what do I mean by a voltage follower? Well, we note here that Vt consists of the ratio of mu divided by mu plus 1, but we saw here that typically for an op-amp mu is very large. Therefore, the voltage seen by the load, looking back here, is essentially equal to the source voltage. So in other words, the output right here follows the input voltage Vs.